This is the henna plant Lawsonia inermis, which is used to make henna paste to dye skin. The active compound in Lawsonia inermis is lawsone, but is not found as a free molecule in the plant. Instead, a molecule called THNG is converted by hydrolysis to THN. This is done by a hydrogen atom replacing the glycosyl group. This then goes through another transformation to lawsone by oxidation. This is done when the henna paste is left out after being mixed. After the henna paste is applied to the skin once more, the lawsone is oxidized again to a red-brown color, which can no longer bind to keratin in the skin like the lawsone molecule can. This is why the experiment done is testing the effect of acidity of the liquid mixed with the henna paste on the oxidation rate and its effect on the darkness of the stain. The longer the paste takes to oxidize, the more lawsone can bind to keratin before it becomes oxidized and can no longer be attached. The liquids being used are tea, lemon, apple, distilled water, tap water. First, the pH of each of these liquids is being tested by using pH strip indicators and being recorded. Then, to get a better consistency of the paste, the henna leaf powder being used is sifted to get rid of any large chunks that could make the henna paste clumpy. Then the henna to each of the containers, 10 milliliters is added to each one. Then 12 to 15 milliliters of the liquid is added, 3 drops of the essential oil, and 3 drops of the honey. This process was then repeated for each liquid. The solvent is used because essential oils are high in monoterpene alcohols, which help facilitate the movement of the lawsone through the paste to more easily dye the skin. The honey is added to improve the flexibility and structure of the paste so that it does not crack as soon as it's put on the skin and isn't too watery. After this is completed, the henna paste were left out for 24 hours to oxidize for the THN to become the lawsone molecule by getting rid of that one hydrogen atom. The henna paste was then placed into henna cones, which were made by cutting out squares from Ziploc bags and folding them into a cone and taping it to secure it. Then the henna paste was applied to the skin, relatively the same thickness and length. Now the lawsone in the henna paste will begin migrating through the paste and to the outer layer of skin, and will begin binding to the keratin in the skin through a process called mycoaddition. This is where the nucleophiles in the keratin will bond permanently to the beta carbon in lawsone. At 8 minutes, some dryness can be seen in the lemon. At 19 minutes, the tap water seems to be the most wet still. The distilled water is beginning to crack. The T and DI water are becoming much darker. The T is beginning to crack. The other pastes seem fine still. Most of the pastes remain pretty wet at 28 minutes. The tea has already begun crumbling, is nearing oxidation. The tap water is beginning to crack, and the tea looks completely oxidized at 31 minutes. At 34 minutes, the DI water looks completely oxidized. At 44 minutes, there is still moisture within the cracks of the tap water and apple juice. The DI water is completely dry at this time. At 49 minutes, tap water is still retaining moisture as well as the apple juice. At 57 minutes, the tap water is completely dry. The apple juice still needs more time. There's a little bit of still wet henna paste in some of the cracks. At 60 minutes, the apple juice is finally oxidized. These are the results of the experiment. The apple juice henna paste had the slowest oxidation rate, followed by the tap water, the lemon juice, distilled water, and tea. These results are somewhat surprising because, in theory, the most acidic solution should have the slowest oxidation rate, because the lower the pH, the more H plus ions, which means that more H plus ions can replace those being lost in oxidation. So the oxidated form of lawsone will be more difficult to form. The reason the moderately acidic solution worked the best may have to do with an overabundance of the lawsone molecule in extremely acidic solutions. Because the solution is so acidic, more TH and G can become TH and thus more lawsone. If there is more of the substance to react, the reaction will happen at a higher rate. Therefore, strong acids don't work as well as moderately acidic solutions. The oxidation rate increases toward a pH of 3 and then decreases after that. This shows that a pH of 3 will give the optimal oxidation time. This is an image of the henna paste after another 30 minutes of oxidation. Most of them seem very cracked, and the lawsone has completely oxidized in the paste. After the paste was washed off, the fast stain created is light orange because this is the color of the raw lawsone molecule, which is bonded to the keratin. Even though oxidation provides a lighter stain if it happens before the lawsone can bind to the keratin, after it binds to the keratin, oxidation will provide a darker stain because the oxidated state of lawsone is a darker color. This is why the morning after the stain appears darker and will continue to darken for the next 1 to 3 days.